Hi everyone, I'm welcome to introduce our work Causal Proxy Models for Concept-Based Model Explanations. My name is Karel Dooserlink, I'm a PhD student from Ghent University, and this was a collaboration with my awesome collaborators Zen, Atticus, Amir, and Professor Christopher Potts from Stanford University. So really, we need concept-based, causal, faithful model explanations for artificial intelligence. The role that AI plays in our daily lives is increasing, and the need for these explanations is increasing as well. Now, what does concept based, causal, and faithful mean? Well, let's start with concept based. An explanation method like GradCam, for example, is not concept based. For a given classifier, an image classifier, this tells us how important input pixels are for the model prediction. And while this can definitely tell us how a model is, what a model is attending to, it really doesn't give us an explanation in terms of these human level concepts we care about, like fur, leash, or eyes, here in the case of animal classification. Contrast this with a work I really like, StyleX, which relates the latent space of a generative model with a classifier in a way that you can study how the latent attributes, here like the width of the pupils of the cat, affect the classifier prediction. So this is already much more intuitive in the human sense. And note how these concepts are really non-trivial functions of the input pixels. All right, so we know what concept-based is. What is causal? Well, causal explanations are causal estimates of the model behavior. Really, the question is, how does the neural prediction on an input depend on a concept? Or if we would change that concept, what is the effect for a given input on the model internals or maybe the model prediction? And last but not least, we need faithful model explanations. At the end of the day, model explanations need to be benchmarked and measured. An explainer is just a method that produces these kind of, in our view, causal predictions about the effect, and that is just something we should measure. And one way to do this is with counterfactual data. So this was something proposed in a recent work called the Kebab dataset. And to validate a bunch of these kind of explainers, they use approximated concept-based counterfactual data. So they have a bunch of inputs that are rewritten by humans to reflect different concepts but have all the rest the same. And that can really be used to benchmark how a model actually changes when going from a factual to a counterfactual. And that is then a validation signal for an explainer that says how important a specific concept was. So we know that we can use counterfactual data to validate explanation methods. But we want to push this even further. We want to use counterfactual data to build better and more robust explanation methods. That's what we set out to do in this work. And we will first show how how causal proxy models are trained on counterfactual data, how they achieve state-of-the-art explanation performance on Kebab, and how intervention training gives causal proxy models causally localized representations, how this is different from normal representations that model learns, and how this can be used for explainability. Let's start with the beginning. A causal proxy model is trained for both factual and counterfactual performance at the same time. Given that we have a frozen model, M, maybe a transformer, that we want to explain, we start by initializing the causal proxy model as a copy of this model. So this is already weird because often an explanation method is typically a simpler approach. Here our explanation method is computationally equally complex as the model we are trying to explain. And then we take our counterfactual training data. And in our training objective, we always have a factual training loss. So that means, given the same input to the model we're trying to explain and the causal proxy model, we want to always expect the same output. We want, in general, for the factual behavior, our causal proxy model to have the same biases, the same heuristics, the same mechanisms of solving the task as the model we're trying to explain. But then we add the counterfactual training loss. So then we give a counterfactual output to the model we're trying to explain, and we observe, a counterfactual input to the model we're trying to explain, and we observe the counterfactual output. And then we train the causal proxy model to mimic this behavior, but only having access to the factual input and a type of description of the intervention. So in the simplest case, this description of the intervention is just a learned token associated with a specific intervention. But really the key here is that this causal proxy model is very similar to the original model, but it is also pushed to predict the counterfactual response of the model we're trying to predict. So at test time, when our goal is, to have an explainer that gives us these kind of estimates of effects, well, we just take the causal proxy model, we input a factual input, we input a description of the intervention, and we hope that it will give us a faithful representation of what the original model would have done in a counterfactual scenario. And that gives us this estimate that we're looking for. And we find that causal proxy models achieve state-of-the-art explanation results on the kebab explanation benchmark. So quickly, how does kebab work? Kebab is a sentiment analysis data set where there are restaurant reviews. You have an overall 5-star sentiment rating, and then there's also 4 intermediate concepts: service, noise, food, and ambience, and those have ternary sentiment ratings: positive, negative, or unknown. And in kebab, the authors take these factual restaurant reviews and have humans rewrite them to create a bunch of counterfactual edits. And in each of these counterfactual edits, the humans are tasked with rewriting the review so that everything is the same except one concept is expressed in a different way. So the table here shows this, but these are shortened toy examples. In real world, these examples are more complex. But the key insight here is that this can be used as validation data for explainers because we actually know how the model will change if the food changes and all the rest is constant. So let's see what actually the metrics are. So on the kebab dataset, there are 4 factual fine-tuned models: BERT, Roberta, GPT-2, and LSTM. So these are models that are just trained on the sentiment analysis task, and we want to explain them with regard to the 4 concepts. Then for each model, we have 3 metrics. Basically, this is just a distance metric between the true effect of changing the concept in the input on the model and what our explainer or what an explainer estimates the effect will be. So these are distance metrics, so lower is always better. And then in our work, because we're all about using counterfactuals to train better explainers, there's 3 strategies of using counterfactuals. There is the strategy that was explored in previous work, which is using no counterfactuals, just using conventional explanation methods. Then we have a way of using sampled counterfactuals. So maybe, getting counterfactual data is expensive. So maybe instead of having humans do these edits, we have some heuristic sampling procedure that we hope, for a given input gives us another input that we think would look like the counterfactual we're searching for. And then last, we have the most expensive method of getting counterfactuals, which is actually tasking humans with creating this very rich counterfactual data. So looking at the results from the previous kebab work, we have one column that aggregates the best scores over all explainers. So this is, I'm not going to go into detail for the explanation methods here, but this is SLearner, TCAF, Concept Chap, Causal LM, and INLP. And then in the separate column, we also just highlighted SLearner, which in general is one of the best explainers they found in kebab. And our first question is, SLearner is not designed to be trained in a counterfactual way. But what happens if we just train it regularly but add the counterfactual data during training? Well, we find that SLearner does not just naively benefit from counterfactual data. Really, there is no kind of explanation improvement. Okay, so let's maybe consider another way of using these counterfactuals as the baseline. Well, one way to do this is to use GPT-3 to write new counterfactuals at test time. So we use the training counterfactuals we have to prompt GPT-3 to teach it to rewrite sentences for specific concepts. And then at inference time, we use this to kind of estimate how the model will change. And we find that actually this produces some good results. So this is really interesting. Of course, this requires using GPT-3, and for example, for real-time explanations at inference time, this might not be scalable. So we explored 2 methods. I'm going to get into detail later, of our causal proxy model, and we find that they are the most performant. In general, across the board, this kind of copy of the original model that is then further fine-tuned for counterfactual behavior is the best at producing explanations when we then have new data and we ask about counterfactuals that the model has never seen before. So we're really, really happy with this. Now, to go further, I want to zoom a bit in on one of these methods to really show you how we achieve this. And that is through causally localized representations. We use a technique called interchange intervention training, introduced by Gagor et al. In 2021, and that promotes causal localization. So what we're going to discuss now is the counterfactual training step, where a causal proxy model is trained to mimic the counterfactual behavior of a black box model. So we have a factual input that goes into the causal proxy model. Then we have a counterfactual input, where maybe everything is the same, but the food changed from positive to negative. That goes into the black box model. And in order to teach the causal proxy model, to mimic the black box model, we need to expose some information about the intervention. And we do this in a really interesting way. We sample a new, completely unrelated review with the only constraint that the food is negative. We then run, a partial forward pass for our proxy model, and then for specific activations, for a slice of activation, so in the model, we have and we associate a slice with the food concept, and then we intervene and we inject the values of that slice on the random inputs with negative food in the causal proxy model on the factual inputs. And then we continue the forward pass and do this distillation loss. But what is really happening here? What we're doing here intuitively is we're promoting the causal proxy model to store all the relevant information about the food concept in these specific neurons. And so really, when we're backpropagating this whole system, we really backpropagate through the intervention in the two forward passes of this causal proxy model. And the really interesting, so this gives the state-of-the-art results you saw on the previous slide, but the really, really interesting result also is that concept-aware feature attributions arise. So what are feature attributions? Well, like using a method like path integrated gradients, we can start asking questions like, hey, how important was this input feature for the model prediction? So let's say we have our causal proxy model, right? There's like an input, a restaurant review, we have the model with tons of representations. We have a few of these localized representations, so representations that we learn to associate with food, ambience, noise, whatever concept we care about. Then we have the output. In a method like path integrated gradients, if you want to know how important the token loud was for the outputs, we kind of consider, the gradients flowing from the output to the input throughout the entire model. We do some operation and then we get an attribution. Now what we propose to do is we propose to restrict those gradients to gradients that flow through a specific representation. So we're not taking like the full gradients, we're really going for gradients mediated by one of these representations that we causally localized. And we're going to show qualitatively what benefits this has. So we're going to do this to a bunch of different explanation models. So as a baseline, we just have a fine-tuned model. This is a model that's trained for the sentiment analysis task, and we didn't do anything crazy with the internal representations. Then we have a multitask model. This is also trained for the sentiment analysis task, but on the specific representations we care about, we put a multitask head and try to predict the related concepts out of these representations. And then we have the interchange intervention model, the IIT model. This is basically the causal proxy model, where instead of multitask training, we did those causal interventions on those specific representations. And so then we're gonna do feature attributions, but not with the full gradients, but only with the gradients mediated by a specific concept. So that means flowing through the neurons that we associated with that concept. And for the fine-tuned baseline, this just gives us a kind of homogeneous attribution. So the model always thinks that, the music was a bad thing because it was too loud, and that friendly and delicious were good words. So these contributed in a positive way to the sentiment prediction. But crucially, whatever kind of mediation we do, we're not seeing a big difference, and which is normal because we didn't train specific representations for this. In the multitask setup, we actually see it's even more homogeneous, which is quite worrying. So even though we trained really classifiers to extract concepts from these hidden representations, we find that the hidden representations actually are not mediating the effect between the input and the output. So this is really this the core insight here is, the issue with probing for explainability is that sure, a representation might contain a lot of information for a given concept, but is not necessarily causally relevant to the model behavior. And then we find that in the causal proxy model, we actually get a completely different picture. For example, for service, the highlight is on friendly waiter. For noise, it is on too loud. For food, it is on delicious. Of course, it's not perfect. Like, for example, for service, the model also highlights delicious in a negative sense. This might be, because our approach is slightly noisy, but this might also really show us maybe some confounding correlations that the model learned and make sure that the model is actually biased in some way. So this is now a really interesting new tool of doing feature attributions with regard to these localized representations to achieve concept-aware feature attributions. So in conclusion, we showed that explainers can be improved by training on counterfactual data. We think that this is a great way forward to just more interpretable AI. Instead of having simple interpretability techniques, really have the interpretability technique be a huge machine learning model itself and directly optimize this for counterfactual faithfulness. We find that causal proxy models, we create causal proxy models to learn to mimic the factual and counterfactual behavior at the same time, and causally localized representations that occur through intervention training give rise to concept-aware attributions. So there's plenty more details in the paper. There's a QR code to the paper, and you can always email the corresponding authors or find me on Twitter and LinkedIn. Thank you very much.